So a very good afternoon to all. It's with great pleasure that today we'll be having Professor Kamesh from University of North Texas in the States. So today he'll be giving us a distinguished lecture related to uncrewed air transportation, titled Autonomy in Airspace. So this is a seminar that is jointly organized not only by the New Zealand North section, but also by the Melbourne and also the Sydney chapters. Right, so with no further ado, please welcome Professor Namuduri.
Very good morning to all of you. Thanks for joining me in this presentation, and thanks to Professor Seat for doing a lot of work on that in the background. My name is Kamesh Namuduri. I'm a professor of electrical engineering at University of North Texas. So our color is green, and then we call it as a mean green. And this work actually has started in 2018 November. NASA called for industry. NASA called all the industry to participate in the project called Advanced Air Mobility. Initially, they called Urban Air Mobility, and then later the name was changed to Advanced Air Mobility. So it began a long time back, and I wanted to share with you the rich experience that I gained over the years. So today's presentation will be at very high level, in the sense, very simple rather. I want to make sure that everybody takes away something from this presentation. At the same time, if you are involved in fundamental research, I'm going to highlight where the topics. For example, actually, I'm going to specify, here is something. Basically, my goal is to make sure that you see the richness in this topic of advanced air mobility and the nature of interdisciplinary research. It's not just technical. It involves, for example, community acceptance. So I want you to appreciate all that, and then let me. I'll do my best. In fact, sometimes our family members are the critics. So my sister told me she's going to evaluate how I do by looking at the recording after that. So anyway, and then I have a kid. I have two children, and my younger kid is 16-year-old. And when I was preparing, all these lectures, she asked me, "You have done the work, right? Why are you preparing?" So that's another perspective. If you did the work on your own, rather you actually engaged in the project, it shouldn't be difficult for you to prepare. But yet I did my best to prepare for this lecture. Okay, so let's see how I do. All right. So thanks to the sponsors, IEEE VTS, National Science Foundation, and NASA, who are providing the funding for this project. And thanks to, of course, IEEE VTS New Zealand chapter. All right. So here is the outline that I have. I'll briefly mention about my university, and then how this project is helping our students at UNT to engage in this state-of-the-art research. At the same time, working with the industry. So this topic, or this research provided an opportunity for especially undergrad students and grad students to engage in the research, and also get to work with the small business industry as well as large industry. And then, in fact, all my students, because they graduated this summer, this spring, they all got jobs, and I had no hard time to find new people to work in my project. It's literally true, because everyone left the school, left the lab, and I tried to encourage them to pursue master's and PhD, but the job is very lucrative. They can't not take the job and do the research. So it's a little bit challenging. But I'm happy that we are able to prepare them very well for the industry. Then I'm the director of the lab called Autonomous Systems Lab. I gave this name way back about 15 years ago without knowing how much work we are going to do. But it would happen that there are so many projects I'm currently involved in. It keeps me very, very busy for a good reason. It's not that I'm stressed out or tired, because this is the work that I like to do. I'm passionate about this work, and I'm seeing good successes. I'll tell you more on that. And then we'll talk about the project of advanced air mobility. What does it mean? And then how I'm able to engage the industry. In fact, it's a partnership between public, private, academic, government, and community. And this is really needed for this problem. The advanced air mobility is something that cannot be done by one group or one company or one university. It's a collective effort. And keep in mind, especially the community engagement and why it is needed. You will see in the lecture. So we call that group as North Texas cohort. And then the main topic of this lecture is autonomy. And I'll tell you, we'll discuss what exactly you mean by autonomy. When you are, in simple terms, if you are sitting in a flight and there is no pilot, then what kind of things you encounter? And we have to envision these problems. We don't know. We can only imagine certain things, certain issues, but in the real world, unless and until you actually see them, see the real flights and do a lot of experimentation, a lot of testing, you won't even know what kind of problems you are going to see. But at this point, we envision the issues that we are supposed to solve and how we are going to solve. You will see a small taste of that. Then we'll spend more time on how to achieve autonomy. What does it mean? And what kind of hardware, what kind of infrastructure you need, and especially what kind of software systems you need. You will appreciate all that. Then and then future research. So that's the outline. So here is a small depiction of advanced air mobility. Many of you might have seen or did some experimentation with small drones. So we have two types of projects, two types of scenarios. One is called UTM. The names do not really tell exactly what they mean, but I will explain. UTM stands for UAS traffic management. And UAS stands for unmanned or uncrewed aircraft system. So we call them as UAVs and colloquially we call them as drones, but technically we call them unmanned aircraft system. UAS stands for UAS. So UTM is a live project that is going on today in some of the cities throughout the world. And there is a global UTM as well. It's not just limited to one country. So, but generally the term is UTM. It stands for this project actually, UTM project is for small drones carrying small packages and delivering to homes. For example, the place where I live in Dallas-Fort Worth, which is designated as one of the key sites by NASA in the US. There are several companies. I know that the last count was 8 companies. Some of them are platform providers. Some of them are retailers. For example, Walmart is one company, is a retail company. And the Wing is a drone company. So, and then UPS, Amazon Prime, I believe. So all these companies are actually fielding, testing. So I have seen, at least some of my students actually have seen, they ordered a small burger and then the drone comes up to the house in the lawn, up to the lawn, or the front yard, and then it drops through a rope or a string, the burger, and then it goes. So initially, they're not charging anything. It's fun to see this small delivery. They're not charging anything for the drone service. So instead of going to the shop and buying a burger, you're asking to the drone company to deliver to your house, and it is fun to watch, and there is no extra charge. It's not going to be that in future, but that's a plan. They're simply testing. So, and keep in mind, these drones are flying at about 400 feet. I put the numbers over here, and that's about 120 meters. Not so high. Okay. And how much weight they can carry? Probably a couple of pounds, not more. And how long they can be in the air? Probably 15-20 minutes. So look at the dimension and parameters. And the other thing is, 15 minutes flight, 15-20 minutes flight, and how far? Probably a few kilometers, not far. So that's it. And that is actually going on. The project started way back in 2014 by NASA around that time. But today it is live in action. And still there are issues. For example, I believe 3 companies are flying, or basically they're sharing the airspace. So they need to figure out how to deconflict. Right? So each company has to know what other company is doing, other drone is doing, just in case to avoid any conflicts. So what does it mean? There should be some sort of a collaborative effort. And by the way, who is doing all this? Who is doing the traffic management? Probably you may know, it's not the government. It's not going to be the federal government or aviation authorities. It's not like ATM or I don't know, aircraft, air traffic management. It's not by the government. So who has to do? Who has to manage that? Federated the organization, means bunch of companies, the company have to come together. They have to work together to find a solution to manage the traffic. So this is in the beginning stages, but it's live. Okay. The next step is what we are actually talking today is about advanced air mobility. It's about flights that are flying in the airspace about 4,000 feet. That means roughly about 1 kilometer, 1.2 kilometer. Okay, you need that much of space because they are large flights. They are helicopter size. They will take people from place to place. For example, we did a test. I'll go and we'll talk about that. So around we haven't gone all the way up to 4,000 feet, but probably about 1,100 feet. We did our first experiment, and there down the lane there won't be any. Very soon, rather, there won't be any pilot. But for now, according to the Federal Aviation Administration's vision, by 2028 they want to see this happen. Again, DFW, where I live, it is going to be one of the important places. And again, there are many places, not many cities, not only in the US, but all around the world. So everybody is working towards it. There are different stages. Maybe something that is what you call confirmed, at least what you call something that you can trust is Federal Aviation Administration's Envision 28. It's actually called. I'll give the exact name. It is by 2028. FAA wants to see these unmanned vehicles in advanced air mobility project. So in between, there will be a pilot, right? So look at the progress, and we call that as crawl, walk, run approach. So just like the way you see self-driving cars, these unmanned or uncrewed aircraft systems are going to start slowly with automation, and slowly in few years we will see these services. We call AAM services. What do they mean? Air taxis, air ambulances, and large cargo deliveries within in some key cities to begin with, and then you will see more and more if the deployment is successful. So what does it mean? We have to make sure that this project is successful. So whose responsibility is that? It rests with all of us. It rests with the industry, with the community, with the researchers like you and me, and also the government. So it's a collective effort. So keep this picture in mind, and imagine that you have these low flying vehicles at 400 feet and large vehicles at 4,000 feet, and try to scale the number and see how does it look like. So what kind of issues you're going to see, and just imagine that you're sitting in this such an air taxi, taking a short flight from wherever you are to nearest airport. So what kind of problems you're going to see? How can we make sure those problems won't occur? Or how do you address those problems? And what kind of research problems are there? So that is the richness I'm talking about. And maybe, some of the problems that you may not even think about include community acceptance, meaning that you can't just fly wherever you want. We have to make sure that the local community is accepting this new technology. That's number one. Number two is, such a technology has to be accessible to everyone. It's not just for rich people. So how do you do that? The good example is Uber. Like everywhere in the world, Uber or equivalent companies are making it available and making it affordable for everyone. And it's cheaper actually to use Uber rather than your own car. For especially in this trip, for example, instead of renting a car and I'm using Uber or Lyft or some other thing. So can we make sure? Can we try to do that? Can we make this technology accessible to everyone? That's a challenge. And the other thing is, where do you put the infrastructure? when I talk about infrastructure, think about the helipads. We call them as vertiports, but really these are like helipads. Maybe 2 or 3 story building, where the rooftop is your for taking you are using that for taking off and landing vehicles. Probably 4 or 8 vehicles with all the power supply, and then of course communication equipment, radar. But where do you place them? It itself is a very interesting topic. You want to make sure that you're putting in a strategic places, not from technology point of view, not only from commercial point of view, from accessibility point. How do you make sure that you are putting this in place? You're creating or building this infrastructure in such a way that it is convenient for people, accessible to people. And the worst thing that can happen is if you don't take care that you are putting all this infrastructure in poor localities, whereas for making all the noise and pollution for certain areas, but giving this the facilities for rich people. So those things have to be avoided. So to keep in mind, how do you do that? It's extremely challenging. So basically what we need is we need to address not only technical challenges, but also about the social issues. Okay. So what did we do in North Texas, where Dallas-Fort Worth is one of the metropolitan area? There are rural areas and also urban areas. We also very close to state of Oklahoma, and there is I used to go there for casinos, but actually later I learned it's a tribal nation. It's a nation called Choctaw Nation. It's a tribal nation. In tribal nation means they have their own government. They don't have to follow federal guidelines, except in some critical scenarios like crime and all that. But otherwise, they're on their own. They're independent. So Oklahoma is also is a rural area. So what we have a great opportunity, I'm going to tell at the end, we want to connect urban and rural areas, and making sure that these services are useful for critical application. Who cares for a burger and a small pizza? What we want to do is make a difference in life, and make sure that instead of, for example, according to a statistic, it takes about 45 minutes to go to a place where if some emergency situation happens in rural area. So can we shorten that to 15 minutes? That makes a good case, right? So these are killer applications. And another application is transportation of human tissues and organs between hospitals. So imagine that there is a donor ready to donate the organ, and there is a recipient in another hospital. And what I heard is, if the organ is out of the body, or a human tissue or organ is out of the body for 1 hour, it might reduce the lifetime of the organ by 10 years. So look at the case, So these are the unimaginable opportunities that we have. It's not just for fun. It's not just for reducing the delivery of a book or something by in hours, 2 hours. But there are very good applications that we can think of. And in terms of research, there are great opportunities and great research problems as well. So what I was able to do is form a group with all these companies, really 15 organizations. And it kind of worked on its own. I talked to one company, and then they talked to other companies, and in fact there are more people who want to join this. So there are big companies like Bell Aircraft, which provided the platform for us, and there are small companies. The Hams is the smallest company with 2 or 3 people only. They built something called a data exchange hub, and it's a spin-off from the university. So we were able to spin off companies from the university because of this work. And a lot of patents are in process. And so I think I'll give you some tour about these projects. One of these companies. One of them is TrueWeather. TrueWeather is a small company, but it has a significant, very important application. It provides what you call micro weather. So it's not sufficient if you get weather from satellites or from airports. We need to know local weather. So there are many ways to do that. For example, you can put a weather station on the drone, on the vehicle, and then each vehicle shares its the weather exact location, and then you can aggregate all this information and share with the drones. That's one big thing. And traffic management, as I mentioned before, traffic management is not the responsibility of the FAA or Aviation Administration. It is the responsibility of the companies. So they are building in the garages. You can develop, for example, a company called Avianco built the traffic management system. And we tested each and every software system, and they worked perfectly when we tested in 2022. So there are all, and Lone Star is a FAA Center for Excellence in Corpus Christi, Texas. They are helping as an operator. All right. So what's the role of university? Why university is involved in this? This is what we do. We provide leadership, research and development leadership to the whole cohort. And we have institute called Center for Integrated Intelligent Mobility Systems at UNT. And that is a cross-disciplinary translational research center that is helping all the faculty from different colleges. College of Science is involved, College of Business is involved. So it's interesting to see how all this faculty, we have about 45 faculty who are working on this. And we look at, I work also in standards development. I'll tell you more on that. And the one I'm passionate about is vehicle-to-vehicle communications for drones. It is IEEE standard 1920.2. We are probably about to release the standard in about 6 months or so from today. And this is what happened in 2022. We started this work in 2018 November, but the actual work started in 2019, and that led to a live demonstration. We haven't used unmanned aircraft, but we used a Bell aircraft, helicopter, as a surrogate. We cannot just, even though there are unmanned systems, unmanned aircraft systems available today, platforms are available, but before we, completely we deploy an unmanned aircraft system in the real world, we had to do a lot of testing with manned aircraft. So that's the reason we did that. And this place is the bottom, the lower circle is Fort Worth Alliance Airport. It's a small airport, private airport. And then on the top, you see UNT. So we don't have a helipad, but we pretended as if we have a vertiport or helipad on campus. So the flight actually started from the Fort Worth Alliance Airport from the bottom, and then there are two paths that you see. So the way it's a nice experiment that we did. So it started from the airport, then on the way, when it is following the right path, we pretended as if there was a hazard in the airspace. So there should be the flight has to be rerouted. So what does it mean? In real time, we send a message from the ground to the drone, to the aircraft, saying that you cannot go in the current plan. You have to change your route. So and remember, everything has to be automated. So that is an example of automated operation. So I'll tell you more about that different operations. I'll actually give you the whole tour of what are the steps involved. But the key idea is that we were able to demonstrate here is without with minimal human intervention, or even complete without any human intervention, it is possible to change the route of an aircraft in the middle of the flight. And then we did 2 times, because of the weather. The second is because of lack of space to land. It always happens. Many times when the weather is bad, you say you cannot land for the airport. So then what happens? Maybe the aircraft will do some rounds and then land, or maybe it will go to some other airport. Same way, we demonstrated that the other autonomous operation where we send a message to the drone that you cannot land at the place that you're supposed to land. You initially plan. So change the direction, go to some other airport and land, some other vertiport in our case. So we were able to demonstrate this critical or very important autonomous operations. And then this article was published in IEEE Spectrum, and it was featured in NASA website. And I have given a UN TED talk in 2022, November, I think. So that was our first success. So there are many things that are going on at UNT. We have several what you call SBIR, Small Business Innovation Research and projects. Direct phase 2 means is about $1 million, 1.25 million. I had 3 projects that I'm involved as a co-PI or a researcher, and these were awarded to companies. So 3 companies received these, startup companies received these awards. And then I have received as a PI, National Science Foundation project called RINGS. CNS stands for Communication and Networking Division. The project is called Resilient and Intelligent Next Generation Networking, RINGS project. That's about $1 million project. We are in the 3rd year. Then NASA MUREP. MUREP stands for Minority University Research Project. And this is given by NASA. The project is about high volume manufacturing. One of the things that we encountered is in the US, almost in every country, is that that some parts, because of many reasons in the supply chain problems rather, you cannot get the part when you want it. So we're trying to look at the problem, so the supply chain logistics, and then also how to manufacture some parts in high volume, because if the project is going to be successful, there is no need to doubt. But when that happens, we need to be ready. That we need to have the parts that are needed to build this aircraft in large volume. So how do you handle that? I think it is almost like supply chain problem has hit every industry, I believe, as I understand. And that project is in collaboration with the College of Business, because supply chain logistics, I don't have any knowledge, even though I served as a PI. It's actually led by a lot of work is being done by College of Business, and that's about $750,000. Then the state level, I received 3 grants from we have something called North Central Texas Council of Governments. So the advantage of this is they lead the community. So all the municipalities, all the local governments are in touch with. It's like a group that connects with all the municipalities. And that's a wonderful collaboration. And we got almost like a couple of $1 million from them too. Then I'm leading 2 standards, and one of them is already released in 2022, 1920.1. It is on airborne networking. It's just a framework, it's not really complete, but it gives a big picture about how to establish aerial networking. And there is another one that's going on, 1954, started recently. It's about agile networking. So it's consistent with the NSF project that I have. So that's kind of interesting that the research and the standards going hand in hand. It's very rare. In fact, I feel so good about engaging in this project, because it's very rare that you see a real world project giving us a research problem. It's the other way normally. We do, for example, think about 5G or 6G, 6th generation networking. What do? You come up with a new modulation technique or maybe new coding techniques, and then the industry picks it up. But this time it's different. The industry is, in fact, moving forward, actually, moving faster than in this area, in this field, to deploy the drones for different services. Now we have seen the challenges. We haven't imagined those problems. And I'll give you in fact, very first problem that I'm working on is, if we go back to this, channel modeling. We have done this in many situations, indoor channel model, or rather, for 5G and all that, right? But here the challenge is this air to air, drone to drone. And I did thorough literature survey, and I see mostly, at universities, we are doing at 400 feet, because that's what we know, that people are thinking, oh, drones are going to fly only at 400 feet. But that's not the case. We are flying at 1,000 meters or 1 kilometer or 4,000 feet. So what will be the channel model? That's a very hard topic. And then you may see people who are in electrical engineering might think, oh, it could be a free space. Not exactly true. So plus the other challenge is, even if you have a very good line of sight, the same thing will cause actually interference problem. Imagine the number of drones or number of vehicles are high. Then it becomes a very, the same strong line of sight will also cause strong interference. So it's a problem, that research problem that we need to look at more carefully. Anyway, this is one problem. And if you are a student, by any chance, make a note of these research problems so that at the end, we'll look at how many research problems that came out of this. Okay, so that's one thing. All right, and then we have a new project called NSF Engines. I'm not the lead, but the College of Business Professor Dean was the lead. This is a very big project. It's a community-related project, or use case-inspired project. The planning grant is about $1 million, but then if we are successful in phase 2, it's $16 million a year for 10 years. So that's pretty competitive and pretty rewarding if we get that. Several patents are in pending, and a lot of spin-off companies, like one company that I'm closely involved is called Hermes Autonomous Air Mobility, and as I mentioned, every student is getting a job. So what are the key challenges? Autonomy is number one, which we'll spend more time to talk about. Traffic management at scale, communication support. It has to be 100% reliable. Well, maybe as much reliability as possible we need to bring. And it needs to be agile. Imagine that two vehicles are in the airspace, and they may be relatively at any orientation. One may be up and one may be down, one may be behind, one may be up. So in all those cases, how do you make sure you have a reliable communication? It is not easy. In fact, it turned out to be the biggest challenge, actually. Then A-to-A conflict management. So one of the things is, obviously collision avoidance, detect and avoid. Look at all these problems. And these are the problems that you may think classical problems or traditional approaches work, but not. These problems are different in airspace. And the time-wise, it has to be real time. I call them as close encounters. Two vehicles are coming so close. I'll show you a simulation later. How do you avoid collision when you don't have time to send a message to the ground and ask for help? You have to do this, resolve this problem, conflict in the airspace in real time. And then security and privacy. Once again, a lot of security people, every time I write a paper or some proposal, I get this comment, oh, security problem has been solved. But it's not. So that means people did not look at the problem, what security problem we have in the airspace. It has to be real time. And one more thing is, it should be what you call agnostic to somewhat, it has to handle this mobility management. Despite the disconnect or connectivity breaks, you still have to work with security. So think about a certificate management, all those things won't work. So we have to have new security solutions. And how do you trust in private in all these things? How do you establish trust in a few minutes? So a lot of issues like that. Okay. Community acceptance itself is a big challenge. Regulations, we don't have regulations yet. So which means that academic researchers, we have to work together, come up with our experiences and then share with the government so that they can form regulations. So far, I have seen, at least in the US, one is called remote ID. So I think it's universal. Remote ID means every drone is expected to share its location to every other drone. And especially for law enforcement agencies, they need to know why there is a drone flying. That's one of it. It's already in practice. It is made turn into a rule in I think in several places, several countries. And the next thing is there are still a lot of room for a lot of regulations have to happen. For example, vehicle-to-vehicle communications. I started in 2017, but then in 2020, 21, industry said, oh, we need this now. So at that time, it was when I reached out to companies, they said, it's in our wish list, but it's not on top of the priority. But fast forward in a few years, like 2022, 2021, 2022, the industry is looking for V2V standards. Once again, we have V2V on the ground, but you cannot just transport V2V standard to airspace. Okay, it is different. The scenario is different. The problems are different. And then suddenly you might see what I call jobs. We need to fill up the jobs. How do you do? Even now, there are few remote pilots. And there is need for pilots in the workforce. And the other thing is the issues like stress, how much stress a pilot faces or feels. How many how many drones a pilot can fly, a remote pilot fly at a given time, how many hours they should be in the work schedule. All these things are all known. So, for example, we are building a behavioral laboratory. It's already there, but we are trying to come up with more facilities to study this kind of problems. It's called cognitive load. It's another term for research. What is the cognitive load for a remote pilot? It is not yet addressed. Okay, I'll try to move quickly so that we can finish in time. So in terms of, these are the technically or technological point of view, these are the problems in terms that we need to look at. Autonomy has three aspects, three pillars actually. One is the platform autonomy. Second is autonomous airspace operations. And then autonomy, infrastructure needed for autonomy. So there are three things. And there's one more thing in the what I call digitized or automated flight rules. Again, it's a job of FAA to come up with these rules. If you are familiar with what I call visual flight rules, we call VFR. Instrument flight rules called IFR. Next time is digital flight rules. So which means that it's still in the very beginning stages. Of course, it's not you and me who develop these rules, but it is federal aviation authorities. They have to develop these rules, which means that we need to provide input to them. Computation, control, sensing. These are technologies that are relevant. So remember, notice this. All this whole electrical engineering discipline is here, and control systems. It's not only part of electrical engineering, but it actually belongs to mechanical and other departments too. By the way, feel free to ask any questions if you have, even in the middle of it. So in terms of communication support, command and control, navigation support. A good example is digital twin. In fact, digital twin, primarily it is from a control point of view, but it's not limited to just control. It could be, you can abstract communication aspects, sensing and computation aspects as well. So I published a paper recently in Open Journal in Vehicular Technology on digital twin for AAM, published in 2013. And in terms of what kind of problems we are looking at, collision avoidance, detect and avoid, collaborative sensing, information relay, and how do you maintain the separation between the vehicles, and merging into traffic. Before we talk about merging, we need to talk about what you call structured airspaces. I'm going to introduce that very soon. Okay, how do you provide this kind of support? You can use cellular networking like 5G and beyond, or dedicated base stations. That means along if you have pre-established the paths or routes, below that paths in the airspace, you need to establish some communication base stations. They don't have to be cellular. They can be some other bands. In fact, at this point, we don't have a frequency band allocated for drone applications. It is 5 gigahertz is being considered even in the US, but nothing is set in terms of what frequency band to use. So you can see where we are, towards making these services, deploying these services in real time. Everything is so close yet so far. That's how we can describe. Yes, in fact, 3GPP release from 17 onwards, if I'm right, is focusing on non-terrestrial networking. But ultimately, they will address the advanced air mobility altitudes as well, which means that they might be focusing now on the lower altitude, but they need to address 4,000 feet as well. It is in progress. We don't have, there are tests being done, but not enough to actually guarantee or assure that, okay, this is enough we have done, and we can provide a reliable service using 3GPP. We are not there yet, but I know that these tests are being done sparsely here and there. For example, I think the NSF project that I was referring to was funded by, the funding is coming from the industry. Nokia is working on that. Ericsson is working on that. So they're all in progress at this point. But while it's a challenge, but a 3GPP is heavily focusing on it, trying to provide solutions for non-terrestrial networking, not only for drones but also for satellite survey. So it is ongoing research. One example that I know, there is a company called Aura Networks. What they are doing is they are using 430 megahertz, and they are creating base stations on the ground. And in our experiment that we did in 2022, we used Silvus radios. Like Silvus radio is a tactical military level grade radio. It costs about, I think, 13,000 a piece. So we bought few of them. Every drone will have, we deployed or we used a radio or installed a radio for every drone. And there is another radio on the ground. So we created a mesh network. Initially, we had problems, but we were able to communicate up to 10 miles, I think, by increasing the transmit power to 10 watts. Initially, it was 1 watt and we were not getting anything. Then by increasing to 10 watts, and even those frequencies were also about, like, I think it's a 2.5 gigahertz. And as part of our National Science Foundation project, my colleagues are working on millimeter wave, but obviously it can't go far. So you can see the challenges. If we want a high data rate, then we go for high frequencies, very high frequencies like millimeter wave, but then they can't go so far. On the other hand, if it is for command and control, you don't need a lot of data rate. It's not really not in gigabits or something. But one thing probably we can do is with the millimeter wave, when the vehicles are close, then you can transmit high data rate. For example, let's say you have some video that you want to share. Then wait for an opportunity for the vehicle to come close within the short distance, then transmit, and then you can. So basically, we want to use both. Maybe frequency bands about like 900 megahertz or so for longer communication, long distance communication. And when the vehicles are close, use millimeter. And my colleague is also working on phased array antennas for beamforming and beam steering. So the problems are, and again, there's another research problem where how do you make two vehicles to have a better line of sight when they are moving fast. So for that problem, the starting point is, we call that as a remote ID. Every drone is supposed to share its location. But by the time you receive the message and process the message, the vehicles already might have moved. So, but you can use that initial location as your approximate location, start steering, beam steering, so that you can have a good alignment maybe for at least some duration. So that itself is a research problem that I'm working on. So this is the second or third, I think I mentioned. Okay, so here is these are the technology issues related to communication. Then again, we'll try to move a little quickly. Societal acceptance. What's the noise? There are noise models that even NASA has produced and they are available. Even for digital twin, just a few days back, I saw an announcement from NASA. They have a eVTOL. eVTOL stands for electric vertical takeoff and landing. The vehicle model is available, and they made it public just a few days back. I was going to give it to my students. So the idea here is, how do you model eVTOL from a control point of view to begin with, so that you are able to see what exactly is happening in the real world on your screen, and vice versa. So the physical model and the virtual model, and they should reflect each other in every aspect, in the sense, especially the control and dynamics point of view. If they reflect the exactly, so whatever you do in virtual model should be communicated to the real physical model, physical vehicle, and whatever is happening with the physical model, you should be able to see in the virtual model. That is really needed for autonomy. So that is something that if you are looking at, you're working on digital twin, that's such a model is available publicly. Right, now let's get into our real topic, autonomy. And more specifically, we're going to look at autonomy in airspace. So 3 things are important. One is platform. there will be occasions when the platform is on its own. It has to figure out how to avoid collision, how to avoid obstacles. So it's not easy. We need to think about what kind of sensors we need. GPS is, of course, what's interesting is without GPS, without getting a GPS signal, in 20 seconds, the drone might get lost. It is, I was surprised to, about 3-4 years ago, I started doing the experiment. Now I talked to the company, and is it true that 20 seconds I'm getting too much error? Yes, that's true. And how commercial aircraft handle? They have alternate mechanisms. But these are, if you're only depending on GPS, then it is possible that in 20 seconds, if you don't get a GPS signal, you might get lost and the drone can crash. So the simple solutions are having 2 GPS, and then you have to come back. Then also, if you're flying on the same path again and again, then you can use some sort of landmarks. But these are not easy. Those people who are working on computer vision, it's not just because you see something on the ground, you know exactly where you are located. It's too much error. I finished the project. I'm about to publish a paper on that, on vision guided navigation for drones. And it's not easy. It's not easy that you fly on top of the building and then find your location. It's not simple, because it depends on the perspective, on height and all that. So that is, and LiDAR. LiDAR is required for distance measurement. Infrared. ADSB is something called it's called Automatic Data Broadcasting Service. It's called ASB. It's a kind of a transponder on the drone. It's also mandatory that every vehicle should have that. So through that, you can actually have some communication. It's not a perfect two-way communication like V2V, but some information about location and negotiation is possible with the ASB. That's about platform. And then in terms of airspace, some key concepts. One is a concept called geofence. Geofence is an area, like a bubble that you create around the vehicle for safety reasons. So basically, you create a fence around the vehicle, and then you want to make sure that no other vehicle is entering that space. So this is good for free flights, like in rural areas. So what we are working on is something called structured airspaces. So we are defining something called an air cell that is fixed. It's almost like a highway on the ground. We are creating highways in the sky, and one of the building blocks is called air cell. And then we talk about lanes, corridors, intersections. I'll show you a couple of examples later. And then traffic management, route optimization, autonomous flight rules, all these things related to airspace management. And then infrastructure, as we talked about briefly before, we need to find, build these vertiports. So in a typical city, you will see maybe, in every municipality, every suburb probably will have one vertiport down the lane. So vertiport again is a landing and takeoff spot or location. And then we need to think about what kind of hardware you need. Communication support, radar to detect what you call non-cooperative vehicles. If it is vehicle-to-vehicle communication, works only for cooperative vehicles. What if the other vehicle doesn't talk? Or maybe it gone rogue and then just flying randomly. Then you need to sense using detect and avoid strategies. So basically you need a radar. At every vertiport, you need a radar and then ADSB support, and then some sort of communication support like 3GPP, 5G or 6G, 5G and 5G and beyond. And then of course, power, charging. Okay, so what do we mean by autonomy in airspace? Let's drill into that. So here, before the vehicle takes off, you need to make plans. So you need to plan a route. For example, let's say, you're going from here to airport. Then the path has to be planned, what we call the set of waypoints. A waypoint is lat long altitude and also expected time. When do you expect the vehicle to be there at that location? So you have to construct a series of waypoints. And of course, there are software tools available, and you can use them. they call mission planning software. And also it's also part of the traffic management system. The traffic management system for advanced air mobility is called PSU. PSU stands for Provider of Services for UAS, or UAM actually. UAM stands for Urban Air Mobility. So these names are names given to these software pieces or modules is not really intuitive. So it's called PSU, but actually its job is to do traffic management. The PSU also can decide the routes. But typically we call it the operator. The job of planning a route is done by the operator. Operator could be like for example, whoever is delivering a product like UPS or Walmart, they will hire some experts in aviation and they will make the plans. So that's basically at the end of the day, it's like a software. Anyone can develop the software, deploy the software from their garage in the cloud and work on it. So there are many companies which are doing that. I know at least about 8 of them. Then, so that's the route planning. The second part is, okay, you might have planned this yesterday for a route, for a delivery that is taking place today, or for a flight that is taking place today. So when the time comes close, you need to get it verified. So who does that? Another system, again, operator sends it to PSU. PSU is the traffic management system. And then the PSU has to talk to weather service to say how is the weather. Then it also has to talk to what you call flight information management system that deals with commercial aviation. So no matter how well we design the traffic system, you cannot have a separated, dedicated route for drones. It's not possible. Because at the airport, for example, you will see commercial aircraft that are flying. So at some point, there will be conflict. So you have to avoid, you have to figure out, you have to live with that. So you will never have a dedicated space for just for drones. It has to share the space, basically, specifically at airports. So that system is called the system that manages commercial aviation, like in Delta, AA, and all that's called flight information management system. So the traffic management system for drones has to talk to the flight information management system to make sure there are no conflicts. These are all in the beginning. So to talk to the weather, to talk to the flight information management system, and there's another piece called directory synchronization service called DSS. So what does it do? It talks about other regions, contacts other regions, and making sure that basically it's just like in the middle, connecting different regions. So for example, let's say our neighboring state is Oklahoma. So the drone is coming from Oklahoma to Texas, and we have Texas. There is another flight going from Texas to Oklahoma. These two systems have to coordinate. So you have to get all these approvals to make sure that the flight path is approved. That means there are no conflicts before it takes off. So that is called acceptance and approval. And then in the middle of the flight, weather can go bad. So even the flight is only 30 minutes, still you have to be ready for those kind of sudden weather dynamic changes. Or maybe something is happening on the ground, maybe an accident, we cannot fly. So those things also we have to accommodate. So what happens is in the real world, whenever there is an event, a dynamic event, we create something called no-fly zone in the airspace. So what's interesting is there is a very well-defined structure or definition of no-fly zone. We call that as constraint. The constraint is a three-dimensional volume in airspace, and we can quickly share. If you look at there is a standard called ASTM standard for constraint or flight path. All these are well defined. So we have all those definitions. All we need to do is follow those standards and build these software systems. And remember, all these systems that we are talking about, traffic management, weather service, or any other like all the DSS I talked about, and then flight information, all these have to talk to each other, which means that you need to develop some APIs. And we use JSON and REST APIs, those who are familiar with that. Okay, and then let's say the approvals are done and the flight is taking place. Then every second, at least once a second, the vehicle is going to tell its location. That's called telemetry. And then The flight path is called operational intent to begin with, or just called flight path for now. And then when you have to reroute, you need to send the same format message to all the stakeholders. And if the drone has to change the route, the operator has to initiate, and then operator has to talk to the traffic management system. Operator has to talk to the weather service, or the traffic management system calls the weather service to make sure that new route is again conflict free. So all those things will take place. And of course, the vehicle has to check, understand the situation in the airspace, and detect other vehicles, especially rogue vehicles, birds. You see, surprising to see, even at 40,000 feet, you can see birds. You can still see birds. So we have to be ready for those kind of things. So what it means is that unlike the small drone that I talked about in the beginning of the seminar, that you can't expect the big drone to land in front of your house and then you sit in. That's not going to happen. We have to walk to a nearby place called vertiport, maybe a mile or 2 miles away, 2 kilometers away, and then you can use the facilities. And
question.
Yeah.
As you mentioned, it's autonomous. So the drones will take the decision by itself, or the controller will lead the drone to land or just fly.
Both are required. Most of the time, they're supposed to be autonomous.
If there is an autonomous,
Okay.
another question is
Mhm.
how the dispatch schedule will be operated, because we are talking about many drones, not
Right.
only one drones
Yeah.
to be operating in the same place.
Mhm.
So if there is many drones are operating in the same place, maybe they are crossing by or traveling through in the same direction.
Mhm.
How the dispatch schedule will be working through?
Yeah, it's
As
called
autonomous.
It's called fleet management. That a lot of companies are already working on that. So, let's say, for example, Walmart or Amazon warehouse, and they're sending. These two are different. These two different companies. They have to coordinate through the DSS, one example that I mentioned, or the PSUs have to talk to each other. PSU means the traffic management system have to talk to each other. But each company, let's say Walmart is sending 1,000 deliveries today. That is done by operator. By operator manages this. So they have to deconflict their own schedules, but at the same time, they have to also deconflict with the other companies.
So in that, there will be little person who is taking all the responsibility for the scheduling, as you mentioning?
It's distributed actually. So in fact, this is exactly happening in my city right now, in Dallas, Fort Worth. I mentioned that Walmart is working on it, and then UPS is testing, and also I believe Amazon Prime. They're all working together. So what happens is their own traffic management systems have to talk to each other. It's a distributed system, not like a centralized.
If the drone takes the autonomous capability,
Mhm.
the drone fly, so still the drone has to take the order from the DSS, all the traffic management system to, shall I go or not?
Yeah, actually, it's the other way. Traffic management system. Let's assume that the operator is about to send a vehicle. Okay, they send their intent to fly with the flight path to the system called PSU, which is the traffic management system, and the traffic management system approves and sends a green signal, and then it takes off. So whenever you are scheduling a new flight, the traffic management system, in this case called PSU, will look at all the existing deliveries, and then make sure that the new flight is not in conflict with any existing. It's possible that other companies maybe has its own system, right? So they have to coordinate through multiple things, like DSS is one thing, and there is a PSU to PSU communication. So basically everything is done through software. So yeah, we'll actually wrap it up. In fact, I think I covered everything that I wanted to say. So here is the question. So if you look at mission planning, okay, and provider of services, we call that a PSU, the traffic management system. On the right side, you see weather service, and then there are other supplemental services called situational awareness service. That means you're looking at the big picture. Are there any failures? Is everything working fine? And then you also see demand capacity balancing at the vertiport. It checks whether the services are available at the landing spots or the vertiports. It's the company called Metron. I think it's Airbus, a spin-off, I believe. They worked with us. Then on the right side, you'll see yeah, the discovery of synchronization, I talked about those, right? DSS and FFINS. So those are from the commercial aviation. DSS is more like synchronization of all these different distributed systems. So all these systems have to work together. And you can see there's a paper that we recently published. You can see this picture over there. And then also here are the steps. How does a flight take off? Operator plans the mission, referred to as operational intent. Basically, it's like a flight path. Then operator submits to PSU, which is the traffic management. PSU shares it with DSS, Discovery Service, and other PSUs because it's a distributed environment, and checks with the weather and the vertiport, whether it can land or not. With all this, after all these checks and balances are done, it will say, okay, you can go ahead. That's the last but one. And then there's authentication also, and all these services are, there should be some token management. And we were able to demonstrate this actually in 2022. And it was like everything, all these systems work like a charm because we worked on it for 2 years, like doing a lot of simulation. And when we actually went for the test, it's like all the pieces worked perfectly. Where we had problem with communication. The radios were like sometimes we were not getting the telemetry. That's because all these issues, antenna alignment. So that's a big thing, but that's my focus. Being an electrical engineer, I'm actually looking at that. But the nice thing is, by doing this demonstration, we understood the key challenges. Software is probably the easiest thing. I mean, it worked because you need to test a lot, but at least that part you can, through simulations, you can see if there is a problem. Authentication, that's fine. All those things are fine. But the communication still remains a challenge. These are all our partners. So many companies we worked. I shared the presentation with Professor Seat, and you can feel free to distribute. And this is something that we are looking at, what we call structured airspaces. I talked about geofence. Geofence is mobile. It's like as the drone is flying, it is created a bubble, and then it wants to make sure nobody comes into my space. But what we are doing here is fixed the airspaces. We are creating a structure in the airspace. These are not mobile, these are fixed. So think about like a nice cube or cuboid, and then you put them like in a sequence and call them as tracks. So, and they have fixed geometry. So you can identify each cell, and for example, you can create a replica like a digital twin on the computer and say which cell is empty, which cell is occupied. All those things you can do. So if you do this successfully, right, then you can actually you can click off a button. You can say how many vehicles are there, how much is the traffic. All those questions you can ask and get answers instantly. And maybe you can also ask complicated questions like how many vehicles are so close. Then once you know the problem, you can fix it too. So those things are possible. And then you can read the paper 2021. We published this idea of air corridors concept in Sensors magazine, a journal. And here is another paper that we published recently, Philosophy of Drone-to-Drone Communication. And this is my lecture in focus around this. This lecture will be in Melbourne, I believe. So just look at the picture is self-sufficient to see. And basically, we are demonstrating the need for vehicle-to-vehicle communications in this slide. And this is another paper that we published. We are presenting in ICC 2024, and I think it's coming next month, June 2024. So we create something called roundabout, like intersection in the airspace, and then how do we negotiate basically, and using. So that's a small simulation. And this is the credit goes to a company called Unmanned Experts. They have done this simulation. They also did this in real world too. The nice thing is some of these tools are so good that whatever you do in the simulation, you can borrow it or you can upload it to the code can be uploaded to the drone, and they behave exactly the same. So that's the power of these tools. Something called ground control is one thing, and there is also Mavlink. So these are the tools people use, and they are so powerful that whatever you do in the simulations can be replicated, can be uploaded to the drone, and they will behave the way we want. So here, the green, red, and so blue are vehicles that are trying to merge in the common lane, and through negotiation using drone-to-drone communications, they were able to deconflict. I think you get that picture. Yeah, we'll take another minute here. My friends, like their names are Shane and my student called Batul. They worked on this and they are presenting this on ICC. I'll skip this and come back to the last few slides. So far I'm showing the lanes and corridors in a nice way, but these are the real corridors that were designed by FAA, Federal Aviation Authorities, and this work is done by NASA folks. Her name is Savi Verma, and you can see this paper. These are the real corridors in Dallas-Fort Worth area. So you can see they're not like so nice, and for theoretical purposes, we can think about cubes and lanes, but in real world, they are not so clean actually. And the numbers that you see, these are the heights, altitudes. So you can read more about design and analysis of corridors for urban air mobility operations, published in 2022 by NASA team. Next slide, please. Okay, this is the future vision. What we have, what UNT or my university has in mind is to connect urban settings like DFW or Dallas-Fort Worth metropolitan areas to rural areas like in the neighboring state, Oklahoma. And those are long distance, about 100 miles. And so on. So it poses some challenges. So what we're trying to do here is have start small, from both ends. So the tribal nation called Choctaw Nation of Oklahoma, they are starting from their end, building small corridors from their side, doing flight tests, and we are doing the same from our side, from Dallas-Fort Worth. And then typically a vertiport consists of, right now we are thinking about like 4, and of course every vertiport needs to have a base station. And then you need other equipment like command and control link and radars. And then at UNT, we're also thinking about creating a behavioral laboratory to study things like cognitive load and all that. So this is a longer vision, probably several years. That's it.
Yeah, I have a question. Thank you for the presentation. To really get to know more information about the UUV. So, like you mentioned that you have done the practical simulation, practically using the military grade communication, those kind of thing. Like, have you tried with the commercial communication kind of thing?
Yeah, the radios are commercial; they're available, but they're expensive. But not expensive when you think in a big picture. Each radio costs about $13,000. It is expensive for us to do some testing, it costs money, but if you for companies, they're not expensive. So those are like point-to-point communication. Okay? On the other hand, if you think about if you work with companies like Ericsson and other service providers, cellular service providers, they need to do some tweaks, obviously, because the cell towers are supposed to be catering the ground communication, right? And providing communication up to 1,000 feet, it may be challenging.
I'm exploring the ideas, instead of going to the point to point, already the base station has been spread out in the city or any locality. Is there research going on modify those things so that they can act as a communication medium with the UAVs. For example, if the UAV is on this locality, to go talk to the specific base station, we went to the other one. That's like one answer.
Like yeah, that is the idea that they are actually cellular companies are working towards. But notice the challenges. So try to see the challenges. One is you need to connect where the flights are going to take place. Let's call them as corridors, right? But cell towers may not be there right there for you. So other thing is the antennas have to be facing the airspace.
Yeah.
So maybe use the beamforming idea, some towards the ground and some towards the air. And also probably you may have to do tracking also, because vehicles, when the vehicles are at a certain location, then maybe the antenna cell tower has to connect to those. So there are challenges, but that is the idea that they are pursuing. A lot of work is going on.
Professor Namuduri, can you hear me well?
I can hear you.
Yes, Professor, excellent presentation. I like the initiative that's being shown. Question for you, though, is that I think a lot of the problems that are being identified were dealt with in the history of aviation. None of these things are new. Navigation without navigation aids was something that was challenging back in the 1930s. The answer to that was landmarks. In other words, using the natural topography. And I noticed that you did say that it's a difficult problem. Yes, for today's AI, it may have some difficulty, but even today, there are AI-powered search engines that are large today, but will be small tomorrow, that you can show them a picture and it will geolocate that picture for you, not having anything to do with the metadata, but just because it recognizes what's in the picture. The scope of this problem is much less than that, because generally you'll be traveling on routes that are known to you or can be known to you on a proving flight. So that's one issue. The next issue is that I am very, very leery of the 5G initiative, because I see that as a play by very rich companies looking to become even richer by taxing via 5G communication this new industry of UAV flight. So I would try to push back as hard as possible against that to do a much safer alternative, because as we know, 5G is not reliable, safe, or available everywhere. The safe alternative is to be able to autonomously navigate to and from the destination without problem. Last issue is that what is the difference between UAV aviation and general aviation and commercial aviation is that UAVs crash a lot, and they will continue to crash, and that needs to be planned in advance. Well-trained commercial pilots always have their crash destination. If they should lose all power right this second, where will they land? That's always known to a good pilot. The pilots that don't fly, that are not professional, don't know that this is the standard, and we are ignoring that to our peril. The last thing the UAV industry needs is a very fatal crash of non-participating citizens because some Amazon delivery needed to take place, and there was no thought, oh my gosh, it's possible that a UAV might crash, which is obvious, of course, in foresight and hindsight. That's why I bring up these requests, is to look into the solutions that were found for general aviation, commercial aviation in the history, so we can avoid being hijacked by corporate interests who are very, very eager to charge by the mile, shall we say.
Yeah. Mithili, I think the Professor Seth is saying that this is going to close. But these are very critical and important issues, and then maybe I will communicate through or email.
Sure.
We can. Thank you for bringing them up.
Thank you.
Thank you for the opportunity. And then I see one more pointer. I'll keep this in mind and then communicate offline. What about mapping the digital? Wonderful. I will take this information from the chat and then try to communicate with each of you.